plates above to move up to several inches a year. Evidence for the theory of continental drift was first proposed in 1912 by German scientist Alfred Wegener. He noticed that identical fossils were discovered oceans away from each other. Paleontologist Professor Mark McMenamin of Mount Holyoke College in Massachusetts is an expert in fossil records.
Wegener noted that a freshwater organism cannot cross a salty sea. And so if you find the fossils of a freshwater organism or a land creature on two continents that are now greatly separated by distance, they must once have been closer together.
By identifying like fossils on different continents, scientists can map which continents were joined in the past.
The fossil distributions will tell us where fossils occur and how the continents must have been juxtaposed. Fossils that are identical but occurring in very different parts of the world imply that the continents have drifted.
When he first proposed his theory of continental drift, Wegener was laughed at. The idea that continents could actually move was considered preposterous. The problem was, he didn't know how the continents moved. The missing mechanism wasn't discovered until the 1960s. Plate tectonics is powered by heat.
Plate tectonics is being largely driven by the fact that the interior of the Earth is much hotter than the surface.
The temperature at the center of the core is 10,000 degrees Fahrenheit. It's as hot as the outer parts of the sun. Much of the heat is left over from the collisions and massive bombardment during the early days of the Earth. The rest comes from radioactive decay of heavy elements in the core. Heat escaping from the core creates convection currents in the next layer of the Earth, the mantle. The process is like a lava lamp, where heat from the bulb at the bottom creates convection currents in the oil, pushing the synthetic lava upward. The heat melts part of the mantle and sends plumes of magma, molten rock, rising to the surface. It rises between cracks in the plates, creating new rock that pushes the plates apart.
I think that plate tectonics is virtually inescapable on this planet. It's an exceedingly efficient way to cool the interior of the Earth.
This formation of new rock splits apart and separates the plates and the continents sitting on them. Today, the majority of this new rock forms under the sea, creating vast interconnected volcanic mountain ranges that extend through all the major oceans of the world. One range can clearly be seen at the bottom of the Atlantic Ocean, along the Mid-Atlantic Ridge. It stretches more than 12,000 miles from the sub-Antarctic to the Arctic. It comes to the surface in a few places. Iceland was created from volcanic lava, bubbling up at the junction between the North American and Eurasian plates. It's one of the few places on Earth that one can actually see continents being pushed apart.
We are watching here geological structures that you cannot really watch anywhere else. It's like a big textbook of geology. This is where the Earth's crust is being made.
Páll Einarsson, professor of geophysics at the University of Iceland, monitors the mid-ocean ridge where the continental plates are splitting apart. The ridge in Iceland is almost 3 miles wide. On one side is the North American plate, on the other side, the Eurasian plate. The rift here grows as new rock forms at its center, pushing North America and Europe away from each other. The Atlantic Ocean widens, and the two continents drift apart. Eventually, the Atlantic could become as big as the Pacific. To measure how fast they're splitting, Einarsson takes global positioning system readings at specific points along the plate margin.
We put the antenna right on top of the point, and then we can calculate the exact position of this point in the world with respect to the center of the Earth.
Although the ridge appears calm and there's no magma rising to the surface, Einarsson's measurements show that the two continents are drifting apart by around an inch a year. So by the end of the century, Europe and America will be almost 8 feet further apart. The movement in Iceland is typical of the processes shaping the continents since their birth 4.4 billion years ago. It's part of the great cycle of the Earth's continents. The new crust, created at the mid-ocean ridge, moves away, cools, and eventually sinks back into the Earth. When the first proto-continents formed, there were several interconnecting tectonic plates, constantly bumping and grinding against each other, pushing the new land over the planet. Today, the Earth has over a dozen plates, some colliding together, some moving apart. They are powerful enough to move a continent the size of North America over 3,000 miles in 200 million years. That's 15 miles every million years. The Earth, 3.4 billion years ago, and plate tectonics pushes the proto-continents together. They combine to form ever larger tracts of land. Scientists suggest that cratons combine with other cratons to form a supercontinent, a huge continuous stretch of land. It's called Valbara. Scientists are unsure of its exact shape or size, as only a few pieces, like the craton in South Africa, still remain. But Valbara's days are numbered. A rising plume of heat is growing beneath it. It's about to rip the world's first supercontinent into pieces. $2.7 billion years ago, Valbara, the world's first supercontinent, still dominates the planet. But plate tectonics, powered by heat from the Earth's core, is about to split it apart. Rock is a good insulator. When a continent gets very large, the rock traps heat beneath it. As it gets hotter and hotter, a plume of superheated magma builds up beneath the giant continental mass. The temperature continues to rise, and pressure in the mantle increases. Eventually, the crust can no longer contain the pressure, and the hot lava breaks through, ripping the land apart. You can see this process happening today in Africa. Heat from the Earth's core is ripping the continent apart. A giant rift valley runs from the Red Sea down to Mozambique. Giant cracks are opening up in the land. Volcanoes, like Kilimanjaro, mark spots where molten rock have risen to the surface in the past. In 10 million years, the eastern half of the continent will have split away. The molten lava trapped beneath the giant supercontinent of Valbara eventually smashes through the surface rock. The continent ruptures into several smaller pieces. These bits of land sail across the Earth. But nobody knows what happens to them or what the planet looks like at this time. The Earth is entering the Dark Ages. It is over 2.5 billion years since it was formed. It will be over 1 billion years before another supercontinent forms. The Earth is entering a deadly cycle of destruction and rebirth.
The theory of continental drift suggests that we go through cyclic phases of continental dispersion and then continental collision. And the continents then seem to move apart from one another and then collide with one another over a maybe 100 million year or more time scale.
When a large continent splits apart, the separate pieces travel away from each other, pushed by the creation of new land at the ridge between plates. Because the Earth has a constant surface area, the same amount of land created must be absorbed into the Earth. This process happens at subduction zones at the junctions of plates. At a subduction zone, crust dives down into the mantle to be melted to form new rock. When the plate subducts into the Earth, it brings two pieces of land together. When they collide, a new supercontinent starts to form. It is now 1.1 billion years ago on our timeline, and the next known supercontinent has formed. Its name is Rodinia, and it holds almost all of the continental rock on the surface of the Earth. Still, no one knows exactly what it looked like, but at its heart is an area that will eventually become North America. 350 million years later, the cycle of annihilation and creation starts again as the buildup of heat beneath the surface of the Earth tears Rodinia apart. When Rodinia splits, it forms several smaller continents that for millions of years drift apart and then drift back together again to form Gondwana, a supercontinent in the southern hemisphere. Eventually, after several hundred million years, Gondwana slowly splits apart. Plate tectonics pushed the land back together to create the world's last supercontinent. It's a huge landmass known as Pangaea. All the continents we know today are here, joined together. Geologists are able to plot the continents' relative positions because 350 million years ago, there are numerous species on Earth, each living in distinct regions.
This specimen that I have right here is the first trilobite that was ever described from what is now the United States. It is exactly the same type of trilobite that occurs on the other side of the Atlantic Ocean in North Africa. So we know then that the trilobites in the old and new worlds must have been close together because they're so closely related.
The fossil records show that North America and Europe rest next to one another. The land where New York now sits is next to Morocco in North Africa. The Atlantic Ocean does not exist. The east coast of South America nestles against the western coast of Africa, while Australia, India, and Antarctica are joined to the southeast of Africa.
If we want to look at a picture of the world 250 million years ago, we're going to look at a world in which a four-footed creature could walk from one end of this landmass to the other.
Pangaea is one giant continuous landmass. It not only makes the world look very different, it also has a dramatic effect on climate. Because much of the land is located far from the sea, the climate of the interior changes radically from season to season. It gets very hot in the summertime and extremely cold in the winter.
You don't have the moderating influence of the ocean that we have today. So it's a very different world. And it's a world that in some ways is harsher and less hospitable, at least to life on land.
It's thought that the climate change caused by Pangaea's formation may have played a role in one of the largest mass extinctions on Earth. This event, known as the Permo-Triassic mass extinction, wipes out about 90% of all life on Earth.
It's been called the mother of all mass extinctions. I would consider that the formation of Pangaea, with its climate worsening effects, to be a contributing factor, however, and not the sole cause of the mass extinction.
250 million years ago, and the supercontinent of Pangaea is breaking up. The continents we know and recognize today begin to take shape. Over the next tens of millions of years, South America drifts away from Africa, North America away from Europe. Australia splits off from Antarctica and heads north to warmer climes. The positions of our continents are becoming familiar, although their distinguishable features are not. The world's vast mountain ranges, the Alps and Himalayas, and its great valleys, like the Grand Canyon, are yet to form. They will emerge out of one of the biggest battles in nature, the battle between colliding continents.